We're going to start right here. Today we teach you a new operation. The operation is function composition. So you know addition, subtraction, multiplication, division. These are all really good things. We've talked about square roots, powers, absolute values, sine, logarithms. These are all operations. So you just need to recognize that there was a time where you were asked to find the square root of 16. And you look at it right now, and it literally takes, about, say 1/10 of a second within your brain to come up with the fact that it's 4. And the question that you ask yourself is, what do I multiply by itself to get 16? But my daughter Tenley, bless her heart, she's pretty good with the whole addition subtraction thing. We're trying to figure out the multiplication thing right now, and the division thing, she has no clue, right? Like, she has no clue. If she were to see this square root thing, she would have no understanding of what it was, right? Like, why does this, like, how do they even come up with the shape? Why are we even using that shape? What does it mean? It's a certain language, correct? So when you see this symbol, it means composition. I'm going to now tell you what that symbol means and what you do with it. F composed of g of x is defined as f of g of x. And here's what happens. You have two functions, multiple functions. You have function g and you have function f. You take x, a domain value, and you plug it into g, you come out with a range value or an output. The output is g of x. Whatever that output is, you take that output and you place it into f as an input. It now becomes a domain value. And it outputs f of g of x. So if you want to know f of g of 0, you start by taking 0 and plugging it into g. And if you plug 0 into g, what do you get? So g of 0 becomes 0. Now you're determining f of 0, and f of 0 is -3. It turns out that multiplication is commutative, meaning 3 times 5 is the same as 5 times 3. But we know that's not the case for division or subtraction, is it? Is function composition commutative? Well, we get a chance to check that out right here. Here you have f of g, now we'll do g of f. So I take 0 and I plug it into f. When we plug f or 0 into f, what do you get? -3. You now take the -3 and plug it in to the g function, and you get 9 minus 6 is 3. So you do not get the same result. Function composition is not commutative. It is not commutative. What's different about letter C? You see this weird symbol, right? They mean the same thing. The only thing different between these two is that in the first one, we're defining it at 0, and the second one, we're defining it at -2. So on the ACT, this is what you would see. They won't write it like that. I'm just showing you both so you understand they mean the same thing. In your mind, you like to think of A, but C is the example you'd actually be given. I take -2 and I plug it in for G. What do you get when you plug in -2 to G? I get 0. Then I take 0 and plug it in for function f, and I get -3. I'd like you to do D, E, and F on your own. Go ahead, try D, E, and F. Go. Okay, for letter D, what did you get? Did you get 35? How about for letter E? -5, and for F? Is there one that people need to look at, or are you feeling okay? Letter D. I'm going to take -2 and place it into F. when I do that, I get negative 2 times 2 is negative 4, minus 3 is negative 7. So it becomes g of negative 7. I take negative 7 and I square it to get 49, and then it's plus a negative 14, which is 35. Better? Any other one? Letter E, f of 1. I take 1 and plug it in. I get 2 times 1 is 2, minus 3 is negative 1. So you then take negative 1 and plug it back into f again. 2 times negative 1 is negative 2, minus 3 is negative 5. What mistake did you make? Okay. So we good? Okay. All right. What's different about letter G? Yeah, there's no domain value. There's just x, right? So if we have f of x is equal to 2x minus 3, and g of x is equal to x squared plus 2x, this is saying to take all of g of x and place it into the x value for f. And when you do that, you get f of g of x is equal to 2 times x squared plus 2x minus 3. Or 2x squared plus 4x minus 3. Try letter H on your own. Please write your answer without any parentheses. So we plug 2x minus 3, you plug it into both spots for x. You get 4x squared minus 12x plus 9 plus 4x minus 6, or 4x squared minus 8x plus 3. Some people in the other classes, their first thought was to multiply the two, okay, and FOIL it out. I understand that it looks like you're multiplying two. You're not. You're composing them. Flip it over. We've looked at some good algebraic examples over the past few days of combining functions and composing them, adding them, subtracting them, doing all those pieces. Now we're going to look at a graphical approach. It says, using the graph, evaluate the following. F plus g of 2. That means you take f of 2 and you add it to g of 2. Look at my graph. F is the blue function and g is the red function. So f of 2 is negative 2. And g of 2 is 2. I add them and I get 0. My next one, g minus f of 0. That would be g of 0 minus f of 0. G of 0 would be 2, and f of 0 would be 0. When you multiply, it's f of negative 1 times g of negative 1. What is f of negative 1? 1. What is g of negative 1? 1. F divided by g of 0. I do f of 0 divided by g of 0. What is f of 0? 0. And what is g of 0? 2. 0's on the top. That's okay. I get 0. Notice how it changes for this. We have f composed of g of 1. So I'm going to do the first one. You'll do the second one. F composed of g of 1 means I take 1 and plug it into g. So I look at the red function. When I plug in 1 into g, I get 3. I then go find 3 and plug it into f. And I get -1. You see that? You try the next one. Try g of f of -2. I was trying to understand why you refused to participate and pay attention today, but you've already seen the lesson, so I'm no longer insulted. So it's like hearing you mess with all yourself. What's going on with I got it. I'll stop judging. All right, I take -2, I plug in for f, and I get 2. I then find 2 and I plug in for g. G is the red function, and I get 2. Did you get it? Not too bad, huh? Can you do this stuff? All right, let's look at our last examples, which is on domain. This is where it gets a little bit more interesting. Not necessarily difficult. It says find f composed of g, and we also want to find the domain. Well, f composed of g is going to be equal to, if you take g and plug it into f, we get 2 over 3 minus x. Look at the original functions. The domain here would be x can't be 0, and the domain here would be all real numbers. Remember when we talked about combining functions earlier, and we said that the domain would be the overlap between the two? Well, if you look, the domain here is not the overlap. It's simply x cannot be 3. Would you agree? So you don't look at the originals. You have to look at the composition. You consider this one. It says find g of f. That means you take f and place it here. And I get the square root of 2x minus 6 minus 2, or the square root of 2x minus 8. How do I find that domain? Two x minus 8 greater than or equal to 0. So 2x greater than or equal to 8. So x greater than or equal to 4. Pretty easy, right? Take out your calculator and flip back 2 pages. Sometimes you just got to have fun. Set aside the crazy math and just have fun. F of g of x, square root of x, and x squared. Those are the 2 things that we have. Okay, square root of x and x squared. So, if we consider this, if we compose, we do f composed of g, you would take this and plug it in for there. And when you do that, you get the square root of x squared. Well, what is the square root of x squared? You would just write x, right? When you're taking the square root of a variable, you need to list both the positive and the negative, right? It's positive x and it's negative x. Now that may seem weird, but I'll show you what it looks like then as we graph it. If you were to look at the domain, you would just look at this and say, well, it's all real numbers. You need to look beforehand, okay? Can you square positives? Can you square negatives? You can square whatever you want, and when you square something, it always becomes positive, okay? So you can take the square root of anything you plug in then, right? Because you're going to get positives. So the domain is all real numbers. Watch what happens when you graph it. If I plug this in, I've got the square root of x squared. If you look, it gives you negative x for that portion, and then gives you positive x right after that. It always gives you those positive results. So many people, when they do this, they would just list x. It gives negative x for the back half and positive x for the front half. So just understand that you sometimes have to look at the composition before you think about it much more. This is interesting because if we flip it the other way, we do g composed of f of x. That means we take this and we plug it in there. And so you get the square root of x quantity squared. Well, you would say that that's x, right? But think about the domain. Can you take the square root of positives? Can you take the square root of negatives? So if you look here, you want to say that the domain is all real numbers, just like the one before. But the fact is that the domain is from 0 to infinity. You can't take the square root of negatives. You have to think about the order in which you're composing them. That is very important. And so if I look at that graph, even though it looks like it comes out to be x, when I graph it, I just get that portion of it. Okay? I don't get the entire line because you only have the positives. This one's pretty easy. F composed of g. I take this and I plug it in for f. I get 1 over the root of x plus 3. If I want to find that domain, I say x plus 3 must be greater than or equal to 0, or x greater than or equal to negative 3. But I have to remember I can't divide by, and what would give you 0? Negative 3. So instead of using a bracket, use a parenthesis, negative 3 to infinity. That's that domain. The other domain is a lot trickier. G composed of f. So that means I take f and I plug it in here. And I get the square root of 1 over x plus 3. How do I handle that? We know that 1 over x plus 3 must be greater than or equal to 0, right? Do you remember when we dealt with nonlinear inequalities, how we solved those? Must have had a bad teacher at that time. 1 over x plus 3x over x is greater than or equal to 0, so 1 plus 3x over x is greater than or equal to 0. This inequality, we make it into one fraction. Do you remember what to do after that? You make a, starts with a T, rhymes with able. What gives you 0 in the denominator? What gives you 0 in the numerator? So I plot negative 1/3, and I plot 0. I'll try plugging in negative 1, and when I do, I get a negative. I'll try plugging in negative 0.1, and when I do, I get a positive and a negative. I'll try plugging in positive 1, I get a positive and a positive. Positive, negative, positive. The question is, where is it greater than or equal to 0? Wherever it's positive. So from negative infinity to negative 1/3, bracket, union with parenthesis 0 to infinity. Because remember, we can't have the 0 in the denominator. That's a pretty involved one. Hopefully you won't see too many like that. Hopefully your teacher takes it easy on you. I think he did, and I think that you'll be able to finish your assignment probably within the hour.